First of all, I would like to thank organizers for very nice. We dropped your ball. Very nice. For this very nice conference, and so I will discuss. The title is a little bit long. So it's black holes and large N species solution to the hierarchy problem. Now the hierarchy problem, as everybody knows by now, is in the standard incarnation is the unexplicable ratio of the fixed mass and fixed mass squared to the Planck mass square. Yeah, something like 32. And the technical problem is that the fixed mass is, as you know very well, quadratically sensitive to the cutoff. Okay? So the thing is, even if you postulate that the cutoff is around the weak scale, you still have to explain why Planck scale is large. Okay? If cutoff is at the Planck scale, then you have to explain what stabilizes the fixed mass. In any case, whatever the solution always comes up in a form of a large UV stable number 10 to the 32. Okay? Now, for instance, in supersymmetry, this is the ratio of the supersymmetry breaking scale to the Planck scale, or in large extra dimension solution to the hierarchy problem is the ratio of it's the large volume of the scale of the scale of the extra dimension, etc. Now, what I want to discuss another approach in which the UV stable number is the number of species, 10 to the 32. Okay. Now, what I will do, I will use the black hole physics to prove exactly the following bound. Now, even if you don't care about the hierarchy problem, this bound still remains exact. So I will prove this bound that in any theory, in any consistent theory in which you have n species at the scale lambda, the Planck scale has to satisfy the following bound. Okay? Now, based on the same proof, actually, we will also prove that the following useful information, that any conserved quantum number that you can imagine in a consistent theory, which is not associated with a long-range classical force, okay, must be defined modulo n, where n is maximum is this, okay, where lambda is the mass of the elementary charge under this whatever quantum number q you have, okay, and this applies to basically any quantum number q which satisfies this condition. Some examples are, for instance, gauge discrete symmetries. So if you have gauge discrete symmetry Zn, n has to satisfy this bound. Okay. If you have a global continuous symmetry, actually you can prove from here that any global continuous symmetry has to be explicitly broken down to Zn subgroup which satisfies this bound. And also, for instance, black hole charges under the massive quantum hair also should be quantized in the same period with the same periodicity. Okay. Now, as far as perturbative approach to the hierarchy problem based on this large N species is not new. Actually, we had this in the paper with Kawadashi, Colano, and Nitti, where perturbatively already sort of there is an indication that if you have n species, because everybody couples to gravity, there is a large renormalization of the gravitational wave function renormalization, and so this generates a correction to the Planck mass, which is n times lambda squared. So if you take n 32, then lambda TV, this will account for the hierarchy. However, the perturbative argument is not an exact proof. So what I want to provide an exact non-perturbative proof of this statement. Okay? Because in perturbative argument, in principle, you can think of some cancellations, or you can think of some bare Planck mass cancelling against the radiative corrections, etc. It turns out this is impossible. So this bound is exact. So now let me discuss this black hole proof. Now, to do it concrete, I'll take a specific situation, okay? Now, consider n species of quantum fields, let's say bosons for simplicity, although it doesn't really matter. So, the 5 j's, and j runs from 1 to n, and let's say they have mass lambda, okay? Now, I will require that these species are, at the moment I require that they are stable, so I require that there is an exact discrete symmetry. Each of them have their own parity, discrete parity, which makes them stable, okay? So in other words, I have Zn symmetry, Z2 symmetry in power n, so in other words, they are different n Z2 factors. Each Z2 factor acts only on one species, and everybody else is invariant, okay? Right? Now, in order to prove this bound, let me do the following thought experiment, okay? Let me prepare a black hole. Let me take the species, the particles from this species, and let me prepare a black hole with a maximal Z2n charge, okay? Now, obviously, because these are Z2s, right? If you take one particle from the first species, that will have a Z2 charge non-zero, two particles will have 0, etc., right? So it's modulo, each Z2 is defined by modulo 1. So the maximal charge, Z2 charge that black hole could carry is n, right? Because when you have, and the minimal such black, to form a minimal such black hole, you have to take one particle from each species. It's very simple, right? So this is the mass of a minimal black hole, which carries n units of the discrete charge. So you take an observer and you prepare, you put n particles together and you form a black hole. Or if you want, you take an astrophysical black hole, existing one, and you throw n particles there. In that case, mass will be higher of the black hole. Now, I want to avoid, because this has to do nothing with this, this proof has to do nothing with this black hole information loss paradoxes and issues. In order to avoid entering discussion in black hole information loss issue, which is very important and interesting point, of course. Think of these Z2s as gauge discrete symmetries, okay? That's the simplest. Now, when you have gauge discrete symmetries, then there is no issue of the information loss, because black holes can carry a Z2, exact Z2 charge. This was first discovered by Charles and Luchek, and it's very well established, because you studied things by now. And you can have an observer which continuously can monitor the Z2 charge of a black hole. Okay, so you can use actually this happens to the Aronov experiment. It's a very interesting topic actually. So you can if you scatter so if you take a black hole through a humongous cosmic string, Z2 cosmic string, you can do an interference experiment, Aronov, and you can detect that there is a Z2 charge inside the black hole, although there is no classical field associated with the Z2 charge. Okay, this is not in contradiction with any no-here theorem or something like that. This is a very well-established fact. Okay, so now we are prepared to do the experiment, because now we have an observer who can monitor this n charge of a black hole, right? And this charge cannot be lost. Okay, so this black hole has n units of Z2 charge, and once the black hole evaporates, it has to give it back. Okay, this n units of the Z2 charge. Okay, very good. So now, this was here. So we have initial black hole. This is time axis, and after evaporation, black hole will emit a bunch of other stuff. But if it's heavier than the minimal, plus it has to give this exactly n species of these particles through the Hawking radiation. And the Hawking temperature, I'll remind you, we had to talk about this, but I'll remind you that it's just n plus squared divided by the mass of the black hole. Okay. Now, the initial mass of the Z2n charged black hole is, as I said, of the minimal one is n times lambda. You can make it arbitrarily heavy if you want. It would be even easier to prove. And n is very large. So then the point is that now I want to prove the bound. Okay. Now, because the n is very large, actually you can take n arbitrarily large. You can make the initial black hole to be arbitrarily heavy. Okay? Big, fuzzy, heavy black hole carrying n units of the discrete charge. Okay? Now, of course, for a big black holes are very cold. So Hawking temperature to start with, I can make Hawking temperature to start with arbitrarily lower than lambda. Okay? So therefore, the point is, so now this is the situation, right? You have an observer. This observer is monitoring the charge of a black hole. And black hole has to start giving back this n quanta of the charge. But it cannot until the temperature falls down to the mass of this quanta. Because the radiation is thermal, okay? I'm only assuming standard things about black hole radiation. So the radiation is thermal, and emission at the temperature, which is less than lambda, of this quanta is exponentially suppressed. So effectively, the emission starts only when the temperature drops down to a certain T star, which is over the lambda. Okay? That's the catch. Okay? So the point is that no matter how many n charges you put in a black hole has no way to give away these charges until the fixed temperature. So that temperature is not scaling with n. Initial n can be arbitrarily large. That temperature is fixed by the mass of the species. It depends. I will show that it only depends logarithmically. Okay, so to the leading order is independent of the charge, whereas the mass of the black hole is scaled as n. The charge scales as n. Okay. So at this point, when the temperature falls down to the mass of the species, the black hole mass is a black hole star, and Planck squared divided by lambda. Okay. So now, from here it's trivial, because now once you have the black hole of this mass, by conservation of energy, at best it can give you the number of species, which is the mass of the black hole, this thing, divided by lambda, and this goes like m Planck over lambda squared, period. Okay? But because charge has to be conserved, the maximum number that black hole can give you back should be equal to n. And so that proves the bound, right? Because the number of quanta emitted is given by this ratio. And so this n maximum has to be bigger or equal to n, and this proves bound. Actually, it makes it even stronger. Okay? So this proves the bound. That n Planck has to be bigger than n times lambda squared. Now, what was the key point of the proof, back to Gabriele's question, is the following. That when I take n to infinity, right, formally I take n for large n, with large n, the black hole mass scales as n, and charge scales also as n, okay? But the critical mass at which black hole can start giving back this information doesn't scale. It scales only as log n, as I will show. Okay? Yeah.
What will happen if we assume that black hole doesn't have a correct result and there is some small result?
Yeah, I'm right. So I'm only assuming standard things about black hole physics. I mean, I'm assuming that. So you know that with remnants there are all these contradictions that you run very quickly, right? Because then. Because sure, yeah, I can prove it in 2 lines. Okay, let's say that you are right, and so what happens is that let's say Slava is right. So what Slava is saying is the black hole evaporates all the way down to the Planck size or whatever size, small size, and then it stores an arbitrarily large information. Okay, fine. So now let me take your remnants and put them together and form a new black hole. So then I can do it forever, this process. And notice that I would very quickly violate Bekenstein-Hawking entropy bound because I would be able to store infinite information in your black hole of a finite mass, right? And all possible contradictions like this. Now, again, if you want to, in this proof I'm assuming that the standard law of the black hole physics is correct. That the evaporation is thermal, and there are no remnants which can store infinite number of information. Okay. Now, if you modify that, of course, then there's a loophole. But I can't imagine any consistent theory in which you can have infinite number of states at the Planck scale, let's say, or somewhere there, which can store infinite information. I can, because of this what I said. Okay. But of course, it's a wild question. I mean, so that defines the conditions of my proof. My proof is based on the fact that the black hole physics is unaffected. It's the standard one.
But in principle, the black hole is a Planck mass. Can have arbitrary large charge?
No, because not with being in agreement with Bekenstein-Hawking entropy. If you want to violate that, that's a separate story by an arbitrary amount. Also, in any field theory of that sort, in which you can have infinite degeneracy of state at a given scale, would be, I can't imagine how we can make any sense of this. But it's obvious that to violate this proof, you have to make something really exotic. I mean, in the non-conventional sense. But I mean, this is absolutely a legitimate question. But I don't think that saves the day. Okay. So now let me quickly discuss this log n corrections. This goes back to Gabriela's question. If we want to be more careful, it's really an easy calculation. But let's make it more precise. This emission process from the black hole, right? So the emission rate of any particular species of mass lambda at small temperature is exponentially separated. Now, so therefore, this is the rate of emission of a single particle. So therefore, the number of the particles, the total number of particles which you will emit from 0 times t star, any time t star, is given by this integral. Then you can do the usual story that we always do, right? Now, on the other hand, we know that this is the rate at which the black hole must decrease because of the operation into massless pieces, gravitons, etc. So, using this and using the fact that the relation between Hawking temperature and the mass, you can convert this integral into the integral in temperature. Okay? And so then you get this integral, and you can take it very easily, this integral. And so now let me integrate to T star, and let me, my definition of T star is that T star is the time or temperature, okay? Capital T is the temperature, till which black hole only emitted order 1 number of particles, okay? Total, of the low species, the massive ones. And I mean, it's obvious if you take this integral and equate n to order 1, you get this condition on T star, and which tells you that T star is not really lambda, but it's actually by log factor log n, actually log n squared, because this is also n, less than lambda. So this actually corrects this bound by log n factor. Okay? So the true bound is actually with log n factor, which I was putting order 1. Now, the question is, okay, now what happens if species are unstable? You can say, okay, so what happens in that case? Now, if species are unstable, then, so let's say they are unstable and their lifetime is Tn, okay? Then, obviously, as long as the lifetime of a species is much larger than the lifetime of the black hole, you can still repeat the same experiment, okay? You put the species in, they just come out, okay? So this gives you an interesting relation, actually. An interesting bound on the lifetime of species. This tells you that, so now, what is the lifetime of the black hole? The lifetime of the black hole is the black hole mass cube divided by m Planck to the 4th. Now, or in other words, let's re-express this in terms of n of the minimum one, right? So this is n cubed times lambda cube over m Planck to the 4th. Now, since the proof is valid as long as lifetime of species is larger than the lifetime of the black hole. But then for the valid proof, I can use this relation and plug it back. I'll get the bound on lifetime of species, which goes like n over lambda. Now, this is a very interesting lifetime, because this is the lifetime exactly of the species which decays through the Planck scale suppressed interactions. Okay? So if they decay through the Planck scale suppressed interactions, then this is the lifetime. So in other words, if species decay gravitationally, you are well within the bounds. Okay? Yeah. So in other words, the lower bound is when the species decay with a Planck scale suppressed interaction. Why? Because if they decay with Planck scale suppressed interaction, the decay rate goes like lambda cube divided n Planck square. Okay? And then converting this back into the lambda, this is lambda over n, and the lifetime is n over lambda. Okay? No, this is a bound on the lifetime of the individual species. Each of them should have lifetime. Yeah. Yeah, but this is accounted by the mass of the black hole. At the end of the day. Yeah. Yes. So. the lifetime of the black hole depends on the cube of the mass, right?
Yeah, it's divided by the number.
Oh, divided by number of species. Okay, maybe you are right. Yeah. Well, that's it. So, but then it's faster. Sorry, then it's oh, sorry. So multiplied by n. Okay, then it makes it even better because then this means that you can have even less stable species which would obey that bound. Oh, that's very good actually. Yeah, that's true. Sorry? Oh, the microphone. This is like the species. Yeah, thank you very much. Yeah, I think that's a good point. Yeah, or maybe I dropped the factor of n somewhere, but I'm not sure. I have to repeat it. Yeah. If there is a factor of n, then this n will go away. So then it means that you are in a, then for any species this will be true, no matter what's the lifetime. Okay, great. Then it's even better. So Slava just strengthened this bound. Okay. Now, what is the byproduct of this discussion? The byproduct of this is what I said. If you have any conserved quantum number, let's call it Q, which is not associated with a long-range classical field, then Q has to be defined modulo n, where n is n Planck divided by lambda squared, where lambda is the mass of the elementary charge. Why? Because you can trivially repeat this proof with any charge, right? It's the same thing. Let's say I have a conserved charge Q. Then I can take n units of the conserved charge, form a black hole, and repeat exactly the same argument. I have to be given back n units, but this is impossible because of this bound. So n has there is a bound of on n, okay, which is the same. So now n could be, as I said, Q can be a Zn symmetry. So for instance, this bound is useful because it tells you that you cannot have, for instance, at Planck scale or close to the Planck scale. Let's say you are at the scale which is factor of 10 lower than n Planck. Your discrete symmetry cannot be higher than Z100. I mean, you may say, okay, Z100 is already good, but still, I mean, your theory will not be consistent unless your Zn is less than Z100, okay? And so on. So there is a strong bound on any discrete symmetry in any consistent theory. Also, this immediately tells you that the baryon, and there is always discussion whether black holes should conserve global symmetries, like baryon and lepton numbers. This is an exact proof which tells you that they cannot. Unless you have a massless baryon somewhere, the baryon number symmetry has to be explicitly broken. Now, of course, we know from string theory that there are other arguments which tell us that these symmetries are explicitly broken in specific string realizations that all the symmetries are gauged. But this is a model-independent argument which tells you that unless, if the lightest baryon is a proton, then the symmetry, the baryon number symmetry, has to be broken down to a Zn subgroup, at least to a Zn subgroup. Of course, it could be broken more, where n is the ratio of the proton mass, Planck mass to the proton mass, okay, into power squared. And the same applies to the black holes with massive quantum hair. Unfortunately, I won't have time to discuss this topic, which is pretty interesting today.
What will be the strength of the grid? Will it be order 1 or continuing out?
No, it has to be order 1 because of this. And if we correct with this lower than n factor, yeah, it will be like order lambda, right? Okay, so for instance, right, if you say, so take a scalar field, some scalar field phi, with mass n phi, and which transforms under the n symmetry. Then, as I said, the black holes, they restrict n to be less than this. Now, you can turn this argument around, and you say, okay, why don't I use this to solve the hierarchy problem? So, take standard model, and then one discrete field, one scalar field which transforms under discrete Zn symmetry, where n is 10 to the 32. And it seems that this solves the hierarchy problem because consistency tells you that the scale has to be separated from the Planck scale by hierarchy. So, in other words, there is a cheap solution to the hierarchy problem that emerges. That you can, in other words, postulate that there are, for instance, 10 to the 32 species at the TV scale. For example, 10 to the 32 copies of the standard model. So let's say there are 10 to the 32 copies of the standard model, all related with the permutation symmetry. And that's it. Then the theory tells you that by consistency, Higgs mass has to be lighter than the Planck scale by a factor of 10 to the 32, period. I mean, so it's a consistency constraint. Now, it's actually yesterday Alex Kusanko came up with a nice comparison because this is like anomalies. It's not about like something being nice or symmetric. It's about consistency. So we know that in spheres anomalies should cancel. This is like this there, okay? In theory, this has to be satisfied. Otherwise, it's just by consistency, okay? Now, the thing is, now, whenever we talk about the solutions of the hierarchy problem, we say that, I mean, usually those solutions are testable at the colliders, at least, right? Because they have to do with the weak scale physics. So the question is, how are these solutions testable at the collider? Actually, it turns out that you cannot avoid testing them at LHC. So if LHC you see nothing, well, of course, if on LHC you see nothing, we'll have other problems. But anyway, I mean, if you don't see nothing, this one, then you can certainly rule these solutions out. Why? And it seems like this is inevitability because of the following argument. Okay. Let me first do the following thing. Okay. Let me first allow. So these are species, this size and air start. How much time do I have, by the way? Okay, great. So these are the size are the standard model species, standard model particles, and let's say these are standard model gauge fields, and they couple to this species. Okay. Now the thing is that let's say you say, okay, let me allow them to couple with certain strength. The point is that this n cannot be lower than the Planck scale. Why? Because if n were lower than the Planck scale, if you allow this coupling, right, then you would have wave function normalization of the standard model fields because of those species. And then you have to explain why standard model is not weakly coupled, is not an extremely weakly coupled theory. Okay? So the maximum allowed strength by which species to couple to us is the gravitational strength. Planckian. Okay? Now, let's say we allow this coupling. Okay, we say let's allow all the couplings which are not forbidden, all the species coupled to us with gravitational strength. So then what happens? Then you produce those species in particle collisions. I don't know, let's say this plus and minus. You produce species in a photon, let's say, or something. The rate of the production of individual of those species is very much suppressed. It's Planckian. But it's enhanced by n factor, and once you plug back the relation between n factor and n, you get this relation. So in other words, at scale lambda, the production rate becomes important. Okay, so you probe them at scale lambda. So it's a general rule. Whether you want to solve the hierarchy problem or not, it seems like that n species that maintain hierarchy between Planck scale and arbitrary scale lambda should be probed at scale lambda. Okay, that's provided they couple with the maximal strength. Okay, now you can say the following thing. So now there's the following puzzle. Okay, I'm still puzzled about it. Maybe you can come up with the solution. Actually, yesterday we were discussing with Salas, and I don't know, maybe he came up with the solution. I don't know. But no, nothing, no news. Okay. Okay, but it's very interesting because let's assume the following thing. Okay, let's assume that these species are not coupled by maximal strength. Okay. Actually, let's say they are completely decoupled. They only couple through gravity. Or in other words, let's write down a theory in which they can only be pair produced at best. Okay? So let's say you have n copies of the standard model, and they can only couple in such a way which is allowed by symmetry. So they can be only pair produced. Okay? So then what happens? So in each copy, now we live in our copy, right? So in our copy we see the Higgs mass where it is. And we are puzzled what stabilizes it, right? So now let's see what happens with the production rate of those other species. And you see very easily the production rate of those other species goes like this, right? So I collide E plus E minus, I produce graviton, and then I produce pair, okay? So this rate it goes like the fourth power of n plus, then I enhance it by n, but n is not helping me because the scale at which I start probing those species, perturbative scale, is geometric mean between the Planck scale and lambda. And this is crazy. Now, why this is crazy? Because somehow theory knows that there must be a hierarchy between scale lambda and Planck scale. But it seems like perturbatively, nothing is happening at that scale. Okay? So you can just bypass it on LHC, will not produce anything. Now, this is impossible. Somehow there should be something wrong with this. This should not be the only argument of production of those species. Now why? Because there is a perturbative argument. In other words, the question is the following, okay? Can it be that actually lambda is not a cutoff of your theory, of your low energy theory? It's just a scale of particles, and you just go through it and go all the way to advanced scale or some higher scale, and nothing happens. And this is this is impossible from the following perturbative argument. Again, the perturbative argument is not an exact proof, but it's still right, because imagine that lambda is not a cutoff, and the cutoff is higher. Okay? Then you are back to square one, because why? Because then you can say, okay, but how can this be? Because now I can again compute the wave function normalization of the graviton through the loops of the species. Okay. Now this gives me n times whatever cuts this loop off. Okay, cutoff square divided by n-Planck square, because I have n-Planck in each vertex. I get this number. But however, if cutoff is much larger than lambda, then this ratio is much larger than 1. And so once I rescale it back, so in other words, no matter what perturbative calculation I will do, at the end of the day, lambda always will be my cutoff in the full rescale sphere. Okay? So the question is how you see it non-perturbatively, that this should happen. And I don't at the moment. Okay? So in those examples, so in other words, there are certainly examples in which you don't see anything obvious going wrong on scale lambda. Now, of course, so the question is this, okay? In other words, where is the non-perturbative obstruction showing that lambda has to be a true cutoff of your theory, okay? Now, the only one I could think of is that what should happen is that the only non-perturbative object that could that could interfere very strongly with the production amplitude at LHC over the scale lambda is through the virtual black holes. Okay, so you produce, if you collide B plus E minus, you produce black holes, some virtual black hole, okay, and then this black hole decays into n species, right? However, the thing is that if this amplitude is the one which tells you that there is a cutoff at lambda, then you are inevitably led to the conclusion that lambda has to be a quantum gravity scale. Because if lambda is not a quantum gravity scale, but any other scale, then why the amplitude of the virtual black hole production will be enormously suppressed. Okay, so then you cannot make up for the rate. So the only way to make up for the rate, the fact that rate actually blows up at scale lambda, is if the virtual black hole production is unsuppressed at scale lambda. But then this means that the lambda is the quantum gravity scale. Okay. So if lambda is, of course, if lambda is quantum gravity scale, then then we can have all the fun that usually we have whenever lambda is the quantum gravity scale at LHC. Okay. Anyway, so I couldn't come up with anything better. So maybe somebody can. So it's finally in remaining, I don't know, maybe 1 minute or something. So there are some open questions. Now, for instance, the open question over there. I mean, these are all obvious open questions. Like, for instance. We are talking about this, why the gut scale is below the Planck scale, there are all these discussions and stuff, right? In the light of this discussion, it's not unnatural to have gut scale below Planck scale. Why? Because in grand unified theories, especially in supersymmetric grand unified theories, the number of species at the gut scale is enormous, right? I mean, for instance, I mean, if I take, as an example, take supersymmetric SO10. I mean, any supersymmetric model builder knows that whenever you start constructing supersymmetric grand unified theories, for instance, SO10, I'm not even going to a higher one. Already here, the number of species is about thousands, okay? Or actually more than thousands. Because you need 3 generations, they have superpartners, then you need 3 copies of fixies, they have superpartners, then you need a bunch of grand unified fixies to break the symmetry, to give neutrinomassives, etc. Once you go into model building, the number of species is enormous. So in other words, in the bottom-up model building, it's usually the number of species at the gut scale is huge. So now this tells you that, of course, gut scale cannot be at the Planck scale. Otherwise, this is inconsistent. This theory would be inconsistent. So there is nothing wrong with the gut scale having lower. Actually, it has to be lower because there are many particles there. Okay. So the question is whether the same applies to the M-Planck and string hierarchy. Now, of course, in the opioid constructions, we know why there is a M-Planck hierarchy, but this tells you that somehow if the same is true about this, we know that there must be this hierarchy, but this is another way to explain it, because at the string scale we have a bunch of particles. But because we have a bunch of particles, this argument tells you that the Planck scale cannot be at the string scale. It has to be higher. And finally, again, the question that I don't know any answer on is that what is the relation between this bound, and the Bekenstein Hawking entropy? I could not read any obvious relation. Okay, but formally, sort of this bound on n formally coincides with a formal entropy of a black hole of mass lambda. But of course, God knows what is black hole of mass lambda, because lambda is much lower than Planck. So I don't know how to interpret that. Okay, I think I can stop here.
In your ultimate comment about the string scale and the Planck scale, you know, in your models, there's a parametric power of the string.
Absolutely.
Do you have any speculation on why there's being n related to that power of 1 over g?
Very good. So now the thing is that there are two arguments, right? The thing is that G string. So I have to think of how this Slava's N correction changes the story. But G string is something that sets the decay rate of those string states, right? So therefore, remember in my argument, it was important that the decay rate of those guys is slower than the decay rate of the corresponding black hole. Okay, so G string certainly plays a role there, because if G string were like 10, these guys would be their decay rate would be faster than the string scale, and then of course this argument could not be applied. The fact that G string is not 1, I don't know what's going on. So the fact that G string is weak, that's precisely why you can still apply this proof. So in other words, you can only apply this proof to the states whose decay rate is slower than their mass. Okay, which means that you can only apply to the weakly coupled states. If they decay like in less time, then this proof breaks down. So that's I think the way the role where the G string plays in this argument. Right? It's just that this whole story has to be consistent, right? Whatever G string tells you and n, they have to be consistent. And in any concrete realization that I know, this is a true story. So everywhere, every time you can check, this is satisfied. Like in large extra dimensions, in Randall diagram, in other string compactifications, always n satisfies this bound.
Well, this is a bit related. I mean, a few minutes ago, I was trying to do such an argument that if you try to make the string strongly coupled at K level, loop would make it weakly coupled anyway.
Okay.
Besides, I got this kind of relation that m string over m Planck to be squared to be 1 over n.
Okay.
It was not a rigorous argument, admittedly, but I wonder, I mean, the proof of the argument seems to indicate that if you try to send a bare Planck mass to 0, then in any way, you reproduce the Planck mass, which will be typically of the order of being cut off at line 10.
Absolutely. Yes.
So this induced gravity
Right.
So I think I agree that the definite proof is lacking because this takes to the same path and so on. I think it's worthwhile to reconsider whether there is a lag coupling limit to strict theory, which is actually an observation that the
Yes, absolutely. Yes, absolutely. Yes, I completely agree with that comment. Yes. So yeah, you're absolutely right. I mean, this perturbative argument suggests that somehow n species want to make gravity weaker by 1 over n factor.
Yeah.
Even if you try to start with strong gravity. So I completely agree with that. So the only thing was that till now there was no exact proof based on record, and this is not perturbative. So that, because in perturbative arguments, I mean, you can always say, oh, maybe there is some cancellation or some fine tuning and stuff like this. But I completely agree. There must be most likely also for if we could resum all the diagrams perturbatively, probably would derive to the same relation. So these two things must be related. Definitely.
Yeah, one more question. Yeah. If there is length 10 to 4,
Yeah.
what should happen in thermodynamics of zero?
Of what?
If you have, for instance, flux in equilibrium with 10 to 15,
Yeah.
what will be the equilibrium energy density? Is
Yeah, you just, yeah, like, I mean, yes, yeah, absolutely. So that's a very, yeah, that's that's a very important question. Of course, the point is this, right? The theories with 10 to the 32 species are not inventing them. For instance, if you take large extra dimension solutions to the hierarchy problem, right, that we have with Salas and Nima, right? So, of course, in that case, we interpret this in terms of this high-dimensional Gauss flow and relation between fundamental and observable and four-dimensional Planck scale. But imagine now we have somebody who knows nothing about it, right? So after this talk, if I tell somebody, okay, here's a theory in which I have 10 to the 32 Kaluza-Klein states, that person immediately would tell me, okay, if there are 10 to the 32 Kaluza-Klein states, the TV scale, Planck scale should be 10 to the TV squared times 10 to the 32, right? So in other words, the theories with humongous number of species are all around. So you know that. Now, what happens? Right. What happens? Yeah, but I mean, sure. But so what if you have an enormous number of states? The thermodynamics will be sort of similar to the thermodynamics of large extra dimensions. That's what I'm trying to say.
There is a gravitational problem. There are 10 to the 32 gravitationally coupled species.
Yeah.
As an analog to the gravitational problem, they would all be the equivalent of one extra regular species. Because it's the same factors that enter. If you like lambda by mt equals squared, that's the ratio of chocolate.
Yeah, but I mean,
you're going to get an extra degree of freedom in the gravity.
Right, but I mean, so far
you can live with one extra degree of freedom, you're okay.
I mean, but now from here to jump to gravitational problem is a little bit right.
You have
what I'm saying is,
32 species, right?
Yeah. So what I'm saying is that
the equivalent to one regular species.
No, they are equivalent to 10 to the 32 species, or one species coupled with one over lambda, right?
Sorry, thermodynamically they're equivalent to one regular model species.
Yeah, coupled with one over lambda.
Right.
Okay,
right.
yeah.
So you are basically, so what I think Sava is alluding to is that the expansion rate, all these bounds on the expansion rate, all that. Effectively, you are creating one extra nuclear species. That's the reflection of.
Yeah, let me clarify that, because you see, when I said large extra dimensions, in large extra dimensions, cosmological issues, they are coming from the fact that the tower of the Kaluza-Klein was starting from the millimeter. Now, here in this case, you can crowd everybody at the TV scale. So I don't want anything. I'm just saying. Look, yeah. For example, right? I mean, this depends on model building. I mean, tell me what is your favorite model to go along this large n, and I'll tell you what will be the consequences. Now, of course, if the thing is that I have n copies of the standard model and I have like 10 to the 2 photons, then of course I will have cosmological issues like I had in the whatever. Yeah, of course, I have to deal with those issues, right? So if I want to just simply postulate that here is a standard model, and then there is a everybody, the rest is at the TV scale, they are all crowded at the TV scale, then there are no cosmological issues. Below TV
marginal. You have one extra nuclear species, effectively.
Yeah, the neutrinos is a separate problem, right? I mean, it's a question of the model building. I don't have anything against it. I mean, model building probably would be a usual mess.
Okay, well, let's postpone further discussion until lunch, which I guess is after the picture.